Do you think?
Okay, as I've been saying, the NPV criteria is a very significant one. We use it in almost all cases. But there are significant uncertainties associated with these three elements that I presented you before in the net present value formula. The first, I mean, it has to do with the income stream because this has to do with the market in which the ship operates for the entire lifetime of the vessel, which can be, let's say, 20 years. And this depends also mainly on the way that the ship will be utilized. I mean, the markets and the trades that it will be serving, the cargoes that will carry, and things like this. On the other hand, the cost stream is also very uncertain as it depends on variables such as fuel prices, which are not known with certainty, but also on uncertainties as regards repairs, maintenance, and other costs. Of course, you are probably aware with the fact that the major part of operational cost is lately bunker cost, and this volatility on fuel prices is a very important one. Last but not least, the cost of capital may not be known through a ship's lifetime. I mean, it is also not constant, and in some cases that lifetime, I mean the N itself is also unknown. So these are some uncertainties that you should have in mind when applying this NPV criterion. And the best in most cases, I suppose, is to perform sensitivity analysis. In case some variables are not known, the sensitivity analysis will give you a range. I mean, it will be extremely easier for you to judge on your investment given this sensitivity analysis. And some other typical pitfalls that you should in any case avoid have to do with, for example, doing meaningless comparisons. If you want to compare two investments, these investments should be kind of similar. You cannot, for example, compare a 50K deadweight bulk carrier with a 100K deadweight bulk carrier. I mean, it doesn't make sense. I mean, on the other hand, you could compare two 50K deadweight vessels with one that is 100K because they most probably they can carry approximately the same cargo, so it makes better sense to do it. The second is that you have to pay attention to the different life cycle durations of your investments. You cannot compare an investment on a vessel for which the lifetime will be 20 years with one for which it will be 30. Or you cannot, I mean, in the same way, you cannot compare easily among building a new vessel with, I mean, the duration of your investment will be, let's say, 20 years, with buying a second-hand vessel for something like 10 years. I mean, that makes no sense. In addition, it is very important to verify the independence of the investments. Sometimes investments are not independent. For instance, two identical ferries serving on a particular market will not necessarily bring double the income of one ferry if the demand is split among these two. So these are some very typical pitfalls, and you should avoid doing them. As you can see, figure 6.2 comes from Stopford's textbook. It shows the various cost compartments of your investment. We have the operating cost, the voyage cost, the cargo handling costs, the capital cost, the interest cost, and the maintenance cost in general. And that is our cost, and the ship revenue is our income. As you can see, the major parts of this investment are the capital cost, which in the case that is presented in figure 6.4. Let me show this to you. Capital cost is almost 42% of the total cost. Similarly, voyage costs are approximately 40%. We are talking about huge cost components, and of that 42%, almost 66%, actually more than 2/3 of the voyage costs are fuel costs, bunker costs. And this is very important, and actually this is the reason why we've seen vessels sailing at lower speeds lately, and this is something that I'll talk about later on. So going back to this basic investment criteria, and this RFR, required freight rate, is another criterion. This is also a major one, and this is a criterion that personally we as naval architects use when we design a vessel. When you design a vessel, you want the ship owner to make a profit out of what you are making, what you are designing. And this is mostly the criterion that we use, the required freight rate, which is defined as follows. We assume that the income of the vessel is equal to the cargo carried multiplied with a constant freight rate. I know that the freight rate is not constant, but that's what we assume. It can be the average of the lifetime of the vessel. We then associate, we kind of calculate the net present value for our investment, having in mind that that assumption is valid. I mean, the assumption I told you about the income, and we then try to find the rate, the freight rate, a constant one, that makes the net present value associated with the ship throughout its lifetime to be 0. So it's a simple equation. You have the net present value. You try to find the freight rate that makes that net present value to be 0. That freight rate is called the required freight rate. And according to this criterion, the vessel whose freight rate is the lowest among alternative ship is the best. This RFR criterion suffers from at least the same deficiencies and limitation as the net present value criterion that I presented before. But in addition, there is another deficiency with this criterion, and it's the fact that RFR is a ratio, and all ratios in general, they ignore scale. So being a ratio, it cannot say anything about the scale of the investment, which actually brings us to the following. Larger ships will typically have a lower required freight rate than smaller vessels due to economies of scale, which actually makes this criterion, which ignores scales, to be in favor of larger vessels. And another problem is that constant freight rate is very seldom. I mean, it will never be experienced by any vessel, with the only exception being a ship that is engaged in a very long-term charter in tram trade. So, when you use this RFR criterion as an investment criterion, the following considerations are very important. First of all, make sure that you compare vessels of similar size. I mean, as you can see in the slide, it makes no sense to compare the RFR of a small feeder container vessel with that of EMA Maersk, which is a huge container vessel. I mean, it makes no sense. In addition to computing the required freight rate, please also try to compute the net present value of the various alternatives. Net present value is a more sound criterion, and my personal opinion is that this is better than the RFR criterion. I mean, RFR is like more easier to communicate with the ship owner probably, but that's a ratio, and as I told you, all ratios ignore scale. It will be good to calculate the RFR, consider the RFR, but also compute the net present value for the various alternatives. And the most important is to make a sensitivity analysis. All major assumptions that enter both formulas, both for NVP and RFR, are uncertain. So the only way to overcome this uncertainty problem is to make an sensitivity analysis, and then it makes it easier for you, for the ship owner, to decide on the best alternative. Another problem is related to what cost and what kind of benefits enter these two formulas that I presented. And it mainly has to do with the person who pays for the cost and the person who receives the benefit. And when you estimate both, I mean, when you use both formulas, you have to consider, I mean, from your own perspective, if you are the ship owner, you have to take only into consideration cost and benefits that are related to you. I mean, in many cases, the charter and the owner are different entities, and some costs are related to one party and some costs to the other. And of course, probably most of you are very familiar with these four types of contractual agreement that are used in shipping. For example, we have the voyage charter, where the ship owner contracts to carry a cargo in a specific vessel for a negotiated price per ton, which covers all the costs. And of course, the voyage has to be completed within the terms of the charter party, else there will be a claim. A variation of this voyage charter is the so-called contract COI, as you probably know it, in which the ship owner contracts to carry regular tonnages of cargo for an agreed price per ton, again covering all costs. However, a time charter gives the charterer the operational control of the ship, while this is leaving ownership and management of the vessel in the hands of the ship owner. The length of the charter can be a single voyage, for example, we call this trip charter, or it can be like a period of months or years, and we call this period charter. And what is important is that when on charter, the ship owner continues to pay the operating cost of the vessel, including crew, maintenance, repair, and so on. But the charterer directs all the commercial operations of the vessel, I mean, like the speed and things like that, and pays all voyage expenses, bunkers, port charges, cargo handling costs, and so on. Finally, we have the bareboat charter, which is kind of financing agreement, because in this bareboat charter, the owner hires out the ship without crew or without any other operational responsibilities. So the owner just pays for the capital cost. It makes an investment, and The charterer is responsible for the vessel for usually 10 to 20 years. He operates it, he makes it profit, and he just gives a kind of rent to the owner who only paid for the capital cost. So he made only basically a financing agreement. So it's just a pure investment, and in most cases these investors are lawyers, are big companies, banks, entities like this, and they have nothing to do with shipping actually, because they don't know so many things about that. They just know they just want to make a profit of this investment. So I'm coming back to the cost breakdown. As I told you, it's very important to differentiate between the parties that pay for the cost and the parties that benefit from whatever benefit can come from that investment. Like, for example, when we are slow steaming, we reduce speed, which means that we reduce fuel consumption, so we reduce bunker cost. And in this case, it depends on the contractual agreement. It depends, I mean, on that agreement, who pays for the bunker cost. So that's the person who will pay less in case that we reduce speed. So I'm coming back to this cost breakdown. There are capital costs associated with these investments. The capital costs have to do with ship construction, retrofitting, major repairs and things like that. Crew expenses have to do with wages paid to crew, overtime, pension, insurance for accidents and sickness, and similar expenses. Vessel expenses are mainly the operational expenses and have to do with paying for the fuel, lubricants, paying for minor repairs, for the annual survey, for freshwater, for communication charges, insurance for hull machinery, risk works, P&I insurance, and things like that. Cargo expenses include when these are applied, cargo inspection, customs examination, various expenses for documentation, staffing, measuring, weighting, and so on. Terminal handling charges are related also, when applicable, to operations like loading and unloading the vessel, delivery, transshipment, storage of cargo, overtime surcharges, and so on. Port charges are related to pilotage, dockage, and other costs, like costs for mooring, unmooring, and so on, that are related with port activities that actually do not have to do with cargo handling. And we also have these administrative expenses, salaries and wages of employees, other benefits, office expenses. I'm not talking for the crew, I'm talking about the expenses that, I mean, besides the personnel that we have on the vessel, we have other personnel ashore, and we probably rent an office, so we have these office expenses. We pay salaries, as I said, for the employees, and so on. We have various legal fees, and other taxes. Some major considerations. One of the major cost components has to do with the building cost and scrapping. I mean, when the lifetime of the vessel approaches, you scrap the vessel, and then you get some money. For shipbuilding, you pay a cost to build the vessel, you save also some money, or actually you receive some money back because of scrapping. And these cost components enter this cost component for shipbuilding and the benefit, the money that you get back from your investment at the end of its lifetime, are very important because they both enter the net present value calculations directly. And as you can see, this figure comes for Clarksons. The new building price for tankers is shown in blue and in red for bulkers. As you can see, the new building price for a vessel is very volatile. It's not something that you can say it's fixed, or it's not something that you can say precisely that you'll know in the price in the next couple of years. And the same goes with scrapping values. When you scrap the vessel, you actually receive some money per ton of steel. They don't pay you for they will not pay you for something else besides the steel value. And actually, that's how we estimate the value of a vessel that goes for scrap. And as you can see, the market is also very volatile, and this shipbuilding and scrapping, the cost and the money that we get back from scrapping, as you can see, we are talking about a market that is very volatile, and you cannot be very precise on what you have to pay. You can actually be it's actually easier to know what you're gonna pay for building a vessel, but it's much more difficult to know what will be the amount that you will receive after 20 years when the vessel will go for scrap. That's the amount of money that you will receive for scrapping the vessel. I don't think it's no. It can be predicted 20 years before. Some other additional considerations. In most cases, you don't have the money to buy the vessel cash. You take a loan, and so loans and interest are two important parameters in the estimation of the net present value. The loans are treated like any other cash stream. Positive for loan receipts to finance part of the construction of the vessel, and negative for repaying capital and interest. A very important parameter is that the loan interest rate is not necessarily equal to I. The I is the one that we use in the net present value, because the ship owner's cost of capital is subject to negotiation between the lender and the ship owner. Another important consideration has to do with the depreciation, which is not a cost that enters the net present value directly, but the connection is mainly through the taxes that are paid, and which typically take depreciation into effect. And regarding taxes that I just mentioned, taxes are also treated in the net present value as an outgoing cash stream. So these were some additional considerations, things that you have to consider when you make this net present value calculations. So I'm now moving to another part which is related to optimizing the economic performance of the vessel, things that can help the ship owner actually receive more money and to make a sound investment. Trying to make money for the ship owner is what people that working in ship companies actually have to do. As I told you lately, in most shipping companies, we have witnessed this phenomenon of slow steaming, which is sailing at speeds that are lower than the design speeds of vessels. Actually, mainly because of the economic crisis. Back in 2007, 110 vessels, container vessels of Maersk Line, started to super slow steam. What is super slow steaming and what these container vessels did? They sailed at actually half of their design speed. Half of their design speed is like running a vessel on 10% of the engine power. If you are a naval architect, you know that when we design a vessel, we optimize it. We assume that the vessel will ship on something like 17 to 85% of the MCR. You probably know this. So these people from Maersk had their container vessels steaming at 10% of MCR, which is an amazing thing, and you can only do it if you have a closely cooperation with the engine manufacturer. That's what Maersk did. They talked directly to the manufacturer. They had what I could call super engine, an engine that can run into that low load, and they saved a lot of money. And they did it because the market was down. They also did it because fuel prices were crazy at that time. But this slow steaming and super slow steaming are this slow steaming is not a new phenomenon. Tankers were also slow steaming during oil crisis back in '97. But recently we had this phenomenon that started with container vessels and mostly Maersk Line containers, and at the beginning of 2011, Maersk had also its tanker fleet flowing at very slow speeds. They had vessels designed to sail at a speed of 13 knots, going down to 8.5 knots on ballast length. You understand that when the vessel carries cargo in the laden condition, it runs fast because it makes profit. But when it's empty, it's what we call on ballast condition, it makes no sense to sail fast. I mean, if you sail slower, it saves you money. And when the market is depressed and the fuel prices are up, that's something that you should do. And actually, the major, at least for me, the major decision variable in optimizing the ship economic performance is speed. This is a very important variable for a variety of reasons. First, speed is the main determinant of fuel cost. And fuel cost is a significant component of the ship's operational cost. And speed is very important because it is directly related to fuel consumption. Probably you've heard about this equation that gives fuel consumption as a function of speed. Naval architects usually use this cubic law between these two. So speed plays a major role in fuel consumption, and I have some slides on this topic that I'll present you later on. Again, speed is also a main factor because it determines how much throughput, and we express throughput in tons kilometer, is produced by a ship, which is directly linked with the lifetime revenue, which means that If a ship sails fast, it will transport more and more cargo. That is the throughput. So you multiply the payload, the tons of the cargo, with the distance that the vessel sails. Actually, it's in miles, but you can transform it to kilometers. And this ton kilometers is a very important thing, the throughput, because that is linked with the ship's revenue. First of all, regarding the optimal speed of vessels, I have to say that the most important thing that you should know, and you probably know, is that ships do not trade at predetermined speeds. This figure comes again from Stopford's excellent textbook, and it shows the supply function for an individual ship, which, as you know, is this so-called J-shaped curve, which describes the amount of transport the owner provides at each level of freight rates. Well, at higher freight rates, the owner speeds up because it makes more money to speed up. But by speeding up, it supplies more transport per year. And for example, in this case that is presented in this figure, by increasing freight rate, the market is obtaining an extra 36% supply. Well, a side effect of that is when freight rates are up and there is overcapacity, things like this, freight rates also go down, which means that actually shipping is more complex than we can describe with this economic approach. In any case, Stopford again presents this relationship between the speed and the freight rate. This S is the optimum speed in miles per day, and is computed given the voyage freight rate R, the price of fuel P, the ship's fuel constant K, and the distance that the vessel has to sail. And this equation defines the shape of the supply curve. As I said, speed is a very important parameter, and in most literature, I think that we have neglected this factor. Very recently, Professor Psaraftis and I, we co-authored a paper. It's a taxonomy actually of speed models, and we took into consideration models that where in which emissions are directly considered, and other models in which emissions are not considered. And we reviewed something like 40 papers on this very important issue, and how speed affects bunker cost and air emissions, which is another topic. And I have a presentation afterwards that is related to these environmental considerations and mostly super emissions. So I'm going back to the optimal speed. Again, as I told you, ships do not trade at a predetermined speed. Those who pay for the fuel, and that is the ship owner if the ship is in the spot market on voyage charter, or the charterer if the ship is on time or bareboat charter. So the owner or the charterer will choose the optimal speed as a function of the bunker price and the state of the market, and more specifically the spot rate. Key is the one that we determine the optimal speed. These formulations are actually this maximization problem for the owner and the minimization problem for the charterer are at the first glance different, but if you do the calculations, you will come to the conclusion that this optimization process arrives at the same thing, which means that the problem, which seems at the beginning to be different, it's actually the same. And in this paper that I mentioned just before, we assumed a fuel consumption function in that form that you can see. Actually, this is a very interesting form because, as you probably know, fuel consumption, as I told you, is mainly related to this factor B and to the ship speed in the exponent of n. In most cases, we assume it cubic. But on the other hand, there is also this constant factor A, because we also have a fuel consumption even when the ship speed goes very low. So assuming that the optimal speed is within the range of the allowable speed vessels, for two distinct ratios Q1 and Q2 that correspond to two optimal speeds, we have estimated this factor. We call it ρ. It is per fuel price divided with the freight rate S. And this chart gives us an idea when the ship owner or the charterer, they'll slow down their vessel. And this is related to the factor R. So if you can compute R, you can know, you can have an estimation on what the ship owner or the charterer will do. I am now coming back to this important topic, speed reduction, and in this figure I present a taxonomy of the incentives, of the reasons why the owner or the charterer reduce the speed of the vessel. So you reduce the speed of the vessel for economical reasons, which are related to high fuel costs and maybe are also related to savings in other costs like port use and taxes, and also mainly when you have low time charter rates. High fuel costs have mainly to do with the volatile fuel market, but also the need in some cases to use more expensive fuel, like for example using low sulfur fuel oil in sulfur emission control areas. Let me explain this to you. As you can see in that figure, there are also there is also a need to cut off emissions. Lately we have this huge phenomenon of having emissions and other environmental considerations affecting the day-to-day operation of shipping companies. And the IMO, the International Maritime Organization, which is the responsible body for all these regulations, has, for example, regulated as follows. There are some regions. We have some regions in the Northern Sea and in the Baltic area, and lately in North America, where IMO has set a cap on the sulfur content of fuel of the fuel that the vessels use. These protected areas where we have set this cap for sulfur, and we have set this cap in order to decrease sulfur dioxide emissions. So in these protected areas, you have to use that cleaner fuel. A fuel that has lower sulfur content than the one that we currently use is a cleaner fuel, but it's also a very expensive fuel. And if your vessel trades into these areas, the so-called sulfur emission control areas, you should use this cleaner and expensive fuel, and this means that you have to pay more for fuel, which is a huge percentage of the operating cost. So in order to avoid paying much, you reduce the speed of your vessel, because by reducing speed, you save on fuel consumption. I'll come back to that later. So that's this figure shows the bunker fuel price. As you can see, the market is very volatile, and it is also obvious that the bunker fuel that most vessels use in their main engines, in blue, it's less expensive than the diesel oil that, for example, vessels use in their auxiliary engines. Auxiliary engines use a cleaner fuel than the one we use in main engine, and this is actually more expensive than the other one. In addition, as I told you, there is the need for cleaner fuel in these so-called sulfur emission control areas, but also there is this EU directive for something like an emission control area for setting a cap in sulfur content for vessels that sail between European ports or while the vessel is in port. Again, we have to use cleaner fuel, which means more costly fuel. Another factor that pushes owners and charterers to reduce speed is the reduced freight rates and the overcapacity, the oversupply of vessels. You probably know that many owners were building vessels in the past few years. Now they are not building that much, and we have a huge amount of tonnage going into the market, which actually as you can see, when when we have an oversupply of vessels, one way to absorb this extra capacity is through reducing the speed. If you reduce speed, you will need more vessels to carry the same throughput per year, let's say. So slow steaming absorbs this overcapacity due to the need of adding more vessels to maintain the same throughput, but this thing leads to higher time charter rates. On the other hand, when time charter rates go down due to low demand and overcapacity, the first reaction of the ship owners and the charterers is to reduce speed. So as you can see, slow steaming is a complex issue, and it has some side effects. In some cases, slow steaming is good for the companies. It's also good for the market because it absorbs capacity. But it does not come without side effects, and the major one is that there is a need of adding more vessels to maintain the same throughput. And I'll get back to that later on. I'll present you the effect of speed reduction by using this model. Let's suppose we have a fleet of n identical vessels, each of which has a capacity or a payload of W. I am talking about a fleet of vessels. In my next presentation, I'll talk specifically for one vessel, but let's suppose we have a fleet of vessels that are of identical size. This is mostly the case. Actually, in some cases, we can see this in liner container market. So let's suppose we have a company that has a fleet of n vessels, and we want to investigate the impact of speed reduction. By reducing speed, we add more ships to maintain the same demand. And in this case, we suppose that the vessel goes from port A to port B in a laden condition and discharges her cargo and comes back in what we call a laden ballast leg. It means empty of cargo, which actually is not a real case, because in reality container vessels do not do this. Tankers actually do this. I mean, going into a ballast, into a laden condition and coming back in ballast. In all other cases, and for sure in container vessels, they don't come back empty, never. Maybe the payload to deadweight ratio is higher when you are coming from Asia to Europe, because you bring cargo from Asia to Europe, and you bring back to Asia less cargo than the one you brought in the other direction. But in this case, we suppose that this fleet of vessels goes into a laden condition, full of cargo, and comes back empty. Regarding fuel consumption, in port, let's suppose that the vessel has a constant fuel consumption of this small f in tons per day. At sea, we know the fuel consumption that the vessel has, and we can calculate the effect of speed change on fuel consumption, assuming a cubic relationship between the fuel consumption and the vessel as follows. The new consumption divided to the consumption when the vessel runs in the normal speed will be equal to this factor. It's the new speed divided to the normal speed in a factor of 3. So you can see when you slow at when the ship sails at slower speeds, there is a huge effect on fuel consumption. I mean, they are directly proportional, but the effect, I mean, there is a major effect when you slow down, even if you go down, let's say, by 1 knot. So that's the reason why we have witnessed so many companies having their vessels sailing at these very low speeds. The basic question that we investigated in a project that I was working on was If all ships of that fleet reduce speed uniformly and the number of ships is increased to match the total demand throughput, I mean to maintain the same throughput, does this lead to a lower fuel bill? I mean, is it also a way to reduce emissions? And the answer is yes. Yes. I mean, even if you have to add more vessels to maintain the same throughput, the effect from the speed reduction is that much that you save money. You still save money, even if you must have more vessels to maintain the same throughput. And that is a very important finding. In addition, you can investigate the optimal speed reduction because for sure you can go down by 1 knot, by 2 knots, but there is an optimal speed reduction, delta V, and for the total fleet. And this is actually, as you can see in this formula, related to the inventory cost, the payload of the vessels, the operational costs, and the distance that the vessels sail. Also related to the fuel price. These are the two possible forms, and you can consider this optimal speed as a cost-benefit speed threshold, and if the original speed of the ship is at or below that threshold, then any attempt to reduce that speed to save fuel and reduce emissions would entail a net total cost increase. But if this is not the case, then slow steaming will be beneficial both for the shipping company and for the environment. There will be savings in bunker costs for the company and reduced emissions for the environment. So everybody is happy. Well, in optimizing fleet operations, speed optimization is not the only decision variable. It is a major decision variable, but it's not the only one. Optimal ship size is another decision variable. Routing and scheduling of the vessels is very important, as it is fleet deployment, choosing the right fleet size and mix, weather routing, guiding the vessel by taking into consideration the weather, intermodal network design, modal split, transshipment, the fact that you have, because of port congestion, to wait at ports, terminal management is also a decision variable that we have to take into consideration. Berth allocation, promptly berthing of the vessels will save time and money, and supply chain management. These are some of the several decision variables that we have to consider when are trying to do some investments or to take some decisions in order to optimize the cost, in order to increase the economic performance of our vessel, of our fleets. So, and now proceed to the last part of this presentation. This is related to risk management. There will be a talk by Stelios Jordanis, I think, on Thursday on this topic. I'll cover, my presentation will be a short introduction to some of the topics that he will present you. When we are talking about risk management, we are not talking about accidental risk and the related subject of maritime safety, which has also economic implications, but we are talking about financial risk. Let me say this personal remark. I did my PhD in risk management, and most people thought that I was doing something like financial stuff. It was economics, but it was not financial risk. It was mostly a risk to human life and a risk to the environment. And that is the accident risk that I told you is related to maritime safety. So we are not talking about this right now. We are talking about financial risk. And the term risk management, when we are talking about financial risk, refers to situations which could lead to a decline in the value of the shipping company, which arises from various events and factors that influence the expected cash flows. If you are interested in this topic, you can go check these two publications from Marizade and Nomikos and Kavousanos and Visvikis. This is major literature on this topic, and my presentation is based on some of the ideas presented in these works. So when we're talking about risk management, one dimension is the price risk. A major component of this is the so-called freight rate or business risk. And this risk is caused by the volatility of the earnings of the shipping company from the freight rates. You probably know, for example, about the volatility of the Baltic Dry Index. There are shipping companies that feel insecurity because of this volatility. How do we deal with this fact? We have these derivatives that have become quite popular as they mitigate market risk via a so-called paper market, where one can open and close long and short positions much faster, more simply, and at a lower cost. Shipping derivatives is a major topic, and as I told you, there will be a specialized presentation on this issue. Another major risk is the operating cost risk. These are related to broking commission, canal fees, maintenance and repair costs, administrative expenses, and other costs. But the most significant factor, as I told you, of the major component of the operating costs are bunker costs. So besides this freight rate variability that I presented in the previous slide, there is volatility also for the price of bunkers, even for a vessel during a single voyage. The price of bunkers is something that you cannot predict. It depends on various things, but it's something that is very important. So if you want to feel secure about this risk, you have these specialized financial derivatives that have been developed. One of these derivatives are the over-the-counter forward banking agreements, where two parties, long and short side, decide on the delivery at an agreed price, quantity, and quality of fuel at a specified delivery location and time. Another risk is related to the interest rate. Interest rate derives from fluctuations in lending rates. When interest rates increase and companies must refinance their loans at a higher rate, we have also companies that may have exposure to currency. If the currency of their revenues is not the same as the one of their debt or operating costs, we have this kind of risks in these operations, and one way to overcome this, one way to feel safe about these risks are the so-called swaps that are used to mitigate interest rate risk, and they are agreements to exchange a series of cash flows on a periodic settlement days over a certain time period, for example, quarterly payments over, let's say, 2 years. We also have this asset price risk. And asset price risk is the risk that comes from the volatility in the price of the assets, which arises from the constantly changing value of vessels. And this hits the balance sheet value of a company as well as its credit rating. In the past, there were no derivatives for vessels, and as short selling of vessels is not possible, one could only take advantage of expectations about an upcoming increase in prices only. But to feel safe, right now we have these sales and purchase forward agreements, the so-called SPFA, for the dry bulk and the tanker markets, and this started back in 2004, and these are traded agreements, and they are calculated in the same manner as the dry and tanker freight indices by the Baltic Exchange. Another risk in our operations, I mean for a shipping company, is the so-called credit risk, which has to do with the ability of a counterparty to pay their obligations, and it's very important in shipping given the cyclical nature of the industry. How can we feel safe about this credit risk? Banks divide these so-called credit enhancements, and they can use master agreements, credit support documents that offer protection against credit risk, credit rating collateralization of transactions. We also have third-party guarantees, credit insurance, letters of credit. All these things can make us feel safe against this credit risk. We also have operational risk, which is the risk of dropping the value of our assets caused by physical damage. That is actually accidents and losses due to physical risks, technical failures, or human errors in the operation of the assets of the company. And when we are saying asset, our mainly asset is the vessel itself. So we have these risks, And for a shipping company, operational risk also includes accidents or liabilities from oil or chemical spillage. That is actually shipping companies are liable for any oil pollution from oil spills that they cause. So if you want to feel safe, there are these insurance contracts in addition to actually better use of technology, which is currently the only solution available to shipping companies. So if you want to feel secure, either you have to use better technology. I mean, when talking about oil pollution, we had these single hull tankers. Now we have these double hull tankers, and that's mandatory. We are more safe because we are using a better technology. We have reduced the risk for oil spills and for paying for any damage that an oil spill could cause. But we also have these insurance contracts that can also protect us against this operational risk. We also have this so-called hedging risk, and this is actually a topic that will be covered by one of the next presentations, so I'll skip this slide. And last but not least, we have these political risks. Any factor that affects the business, which is caused by political events like wars, political turmoil in a region, canal closures like the Suez Canal, are included here in the political risks. And these events have always affected the international trade and shipping, and have also affected the global economic growth. In recent cases are the World War, the Second World War, the Suez Canal closures, and the Gulf Wars. And as you can see these major increases in the price of fuel oil, one in here and another in here. These are related to some political events that have to do, for example, with the Yom Kippur War. Probably you may be familiar with this conflict between Israel and the Arabs. These events affected oil price extremely, and the truth is that even after these extreme events that caused this extreme increase of fuel oil prices, these prices, they never went back down as much as it was before. And you can see these prices are per barrel, if I am not wrong. That's the price right now, and that's the price, let's say, 40 years ago. Nobody cared about speed reduction or things like this, or about the operational costs, because fuel prices were extremely low. Now fuel prices are up, and they'll stay there, and this makes bunker cost the most influencing operational cost. And with that, I want to close my presentation, and as a summary, I attempted to highlight a rather limited number of issues in shipping economics. environmental concerns about air pollution from ships and the need to reduce them. It is imperative to improve the economic performance of ships to the greatest possible extent. And I didn't talk much about this except the part that was related to speed reduction, but and environmental criteria therefore were not examined explicitly in this chapter. I'm in this presentation, and again this presentation draws from a book chapter that I have co-authored with Professor Psarafis and Associate Professor Liridis, and you can find it in our website. But as CPR emissions are directly proportional to fuel burned, it is clear that minimizing fuel consumption would also minimize emissions. So thanks for being here in this first presentation. My next presentation will be shortly after a break, and we are moving from ship economics to what I call shipping carbonomics. Shipping carbonomics are shipping economics in a carbon-constrained world. It is the world, the situation that we are living on. It is something that will affect us in the near future. So, thanks. I don't know if there are any questions regarding my presentation. Do we have time for questions?
Okay.
So please, if there are any questions.
Jacob in general. No questions.
Okay, there are no questions. It means either that you understood them all or nothing. Okay, then let's have a small break for 10 to 15 minutes. There is coffee outside and cakes and other things. Let me again thank people that are online, and we'll come back in a few minutes. Okay, guys, you have 10 to 15 minutes for this break. So to our friends that are watching this online, we'll have a short break in here. I wish you were here, and thanks for watching this presentation. I'll come back soon with the introduction to shipping carbonomics. Thanks. Okay, hello again. This is my second presentation. It is entitled An Introduction to Shipping Carbonomics. As I told you before, my definition of carbonomics, of shipping carbonomics, is shipping economics in a carbon-constrained world. And my talk is mainly on the environmental regulations and how they affect the operation of shipping companies. As you probably know, there is lately a drive for cleaner shipping. Shipper emissions actually are very high on the agenda of the International Maritime Organization. This topic is also very high on the agendas of the European Union and individual coastal countries. The top priority is the reduction of shipper emissions. So the first part of this presentation is related to how can we estimate the emissions from ships. If you want to estimate the carbon dioxide that is emitting from a vessel, you have to multiply the fuel consumption in tons, that can be per year, per day, per trip, with this so-called CO2 emission factor. And this factor depends actually on the fuel that is used. There is a different factor for marine diesel oil and marine gas oil, as you can see in that table. And there is also different emission factor for low sulfur fuel oils and high sulfur fuel oils. But actually in the past few years, we used a single value, this 3.17 figure that you can see in there, which means that when a ship burns 1 ton of fuel oil, it produces roughly 3.17 tons of CO2. If you want a more accurate estimate, you can use the CO2, the carbon dioxide emission factor that based on the fuel that you are using. Regarding sulfur oxides, main part of this is of the so-called SOx emissions is sulfur dioxide, SO2. These are mostly related to the sulfur content of the fuel that you burn, multiplied with this 0.02 factor, which actually comes from the which is exact and comes from the chemical reaction of sulfur and oxide. Regarding NOx emissions also depend on fuel consumption, but the ratio of NOx emissions to fuel consumption, it varies from 0.087 from slow speed engines to 0.057 for medium speed engines. So SOx emissions are related to the sulfur content of the fuel. NOx emissions are related to the engine that is used to burn the fuel. Bunker cost is directly related to fuel consumption. As I told you before, MDO, like diesel oil that we mostly use in auxiliary engines, is much more expensive than the bunker fuel that we use in main engines. And fuel prices are extremely volatile, as you can see in that figure. And what is extremely important is that both bunker cost and shipper emissions are directly proportional to fuel used, which means that if you save on fuel consumption, you also save on bunker cost and so on shipper emissions, which means that reducing, actually the bottom line is that reducing speed or with any other measure, if you can reduce fuel consumption, you reduce the bunker cost, which is good for the company, and you reduce emissions, which is good for the environment. So we have a so-called win-win situation. What are the true effects from air emissions? Well, this is a figure that comes from a paper that I have co-authored with Professor Psarafis, and this is an estimation of the total CO2 produced by the world commercial fleet. You can see the amount of CO2 emissions emitted by specific by vessels per vessel category. It is extremely interesting the fact that this single category, the post-Panamax vessels, which are container ships, 4,400 TEUs and more, this single category produces the same amount of CO2 emissions as the whole tanker fleet. Why does this top tier container category emits that same amount? Because of the high speed, of the high design speed. Container vessels may operate at a speed of 21, 24 knots. Tankers can be from 13, 14, that much slower. The same is also true for passenger vessels, for RoPax. They are designed to sail at higher speeds, but they aren't that many. That's why the CO2 amount from that category, from RoPax vessels, is not that huge. But as I told you, this thing with container ships is a reality, and that's why we've seen so many container vessels slow steaming. Well, we are not sure about the total amount that shipping emits in terms of CO2. IMO asked a group, actually tasked a group that was led by Marintech in Norway to estimate the total emissions produced by the world fleet. So the total CO2 emissions from shipping are estimated to range from 854 to 1,224 million tons per year. That's for 2007, with a consensus estimate of something like 1 billion tons. So roughly, shipping emits 1 billion tons per year. That is that figure is for 2007, and it goes up. As you can see, transportation, 27.7% of the world's CO2 emissions comes from transportation. 21.3% of those emissions are from road, 2.6% from aviation, 0.5% from rail, and 3.3% from marine transportation, and actually 2.7% comes from international shipping. That's the contribution of shipping to the total CO2 emissions. Do you want to compare CO2 emissions from vessels with other transport modes? That's the chart. You can see shipping is a clear winner. That's the amount emitted from a Boeing 747. That's for a truck, that's for a diesel rail, and that's for a Capesize bulk carrier. So in total, 2.7% of the total CO2 emissions, anthropogenic emissions, come from international shipping. Shipping carries approximately 90% of the world trade, which means that is the least, that is the best, the most efficient mode, the most efficient transport mode, and that makes shipping a clear winner. Well, this does not mean that shipping does not affect the environment and human life. Shipping does affect humans and the environment, and we have to do something about this. And besides CO2 emissions that can lead to climate change, we have NOx emissions that contribute to the formation of photochemical smog that leads to elevated levels of ozone and the production of other hazardous organic compounds, and together with SOx, SOx and NOx affect air quality, and they contribute to acid rain. So that's how they mainly affect the environment. SO2, sulfur dioxide emissions, also affect human lives directly by affecting lung function. So they harm human health. Why do we focus on CO2 and ozone, which are greenhouse gases? Because both of them are related to climate change. SOx and NOx are not related to climate change, but are related to other problems, as I described previously. Well, the major problem with carbon dioxide emission is that they cause global warming. But in addition to global warming by CO2, ship emissions of sulfur dioxide cause cooling through effects on atmospheric particles and clouds. NOx emissions also increase the levels of ozone, which is a greenhouse gas, and reduce methane, which is another greenhouse gas, causing warming and cooling respectively. This means that as a result, the net global mean radiative forcing from shipping currently is strongly negative, which actually means, in plain English, that shipping does not is not related currently, is not causing currently warming. But this is going to change, and this will change definitely due to these new regulations regarding sulfur dioxide emissions, because setting a cap on the content of sulfur on fuel oil will lead to producing less CO2, and we will not have this cooling effect that SOx is providing. Let me make myself clear. SOx is bad when we emit it near cities, because it causes acid rain. And in Greece, we know that, for example, the statues in the Acropolis, the Caryatides, for example, are fake. The ones that we have in the hill. The real ones, except the one that is missing, is in the Acropolis Museum. Why that? Because of acid rain. I mean, if you can see the statue, you can see the effect of acid rain in that statues. So it is affecting the quality of of our life, and is also affecting our heritage. Acid rain is a huge problem, and SOx emissions are definitely a huge problem. But this is something that we have to have in mind, that SOx emissions do also have another effect, and I am in favor of having something like a more holistic approach to CPR emissions. Well, now I'm moving to how we regulate CPR emissions. Probably you know that the International Maritime Organization is the single authority that we have in shipping for setting these global regulations. Of course, we have other regional regulations, but IMO has set these standards for NOx emissions. And to control NOx, the IMO has this MARPOL regulation, which has these standards based on the speed, on the RPM of the main engine. So there are some limits on NOx emissions based on the rated engine speed. For NOx, we do have these caps on the sulfur content, like there is a global cap of 4.5% of sulfur in all fuels that we use in shipping, and we have these emission control areas where the cap on sulfur content is much lower, and this is expected to become lower and lower and lower, and this means that in shipping we'll have to use more cleaner and more expensive fuel. Eventually we may be forced to use something like diesel oil, like the one that cars are using in ships. You probably know that ship engines are not designed to burn diesel oil. They're designed to burn heavy fuel oil. There are of course some problems with that, but the regulation, I mean, there is a tendency to setting lower limits on sulfur content. And we have these so-called emission control areas, the Baltic area and the North Sea, where we have existing ECAs with limitation on sulfur emissions, and we have the North American coast, which is a very new emission control area, has very recently introduced, and we have regulations that set cap on sulfur emissions, and we have also these NOx limitations. We also have limits set by the European Union, and there are other regional regulations. For example, in the US, there are also some regulations on NOx and SOx mainly. Let's go back to carbon dioxide. Carbon dioxide is, you have to understand that NOx and SOx are not greenhouse gases. Carbon dioxide is a bad thing because it leads to climate change, but carbon dioxide is not a pollutant. It is a naturally occurring gas. I mean, right now I'm producing CO2. It is a byproduct of burning fossil fuels and of land use changes and other industrial processes. But as I told you, it is the principal anthropogenic greenhouse gas that affects the Earth's radiative balance, and that leads to climate change. Well, although some regulations exist for non-greenhouse gases such as SOx and NOx, the regulations that I presented previously, shipping has escaped being included in the Kyoto global emissions reduction target for CO2, And until now, there were no regulations regarding CO2. There were no regulations. This has changed, actually. Let me first present you some measures and policies to reduce SIPR emissions. There are various measures that can be used to reduce emissions. Technological measures like having more efficient and energy-saving engines, more efficient ship hulls, more efficient propulsion, using this so-called cold iron in ports, by using alternative fuels, for example, fuel cells and other measures. And we have these operational measures like speed reduction that we discussed previously, and it will be the major part of my next presentation. We also have these protected areas that I mentioned earlier, and we have these market-based measures or market-based instruments, as it was the name used in the past few years, that I will present to you later on. This table presents an overview of policies to limit or reduce emissions of greenhouse gases from ships. Regulations introduced by the International Maritime Organization. We have these market-based instruments, which are essentially a tax on emissions or bunker consumption, and this so-called emission trading. I'll come back to that soon. And we have this EOI, which is the so-called energy efficiency operational indicator, and this EEDI, which is the energy efficiency design index. This is an index for new vessels. This is an indicator for existing vessels. We have tax and trading, which are part of market-based instruments, and we have this so-called CEM. And this is how the era of non-regulation for CO2 emissions ended in shipping. We have the introduction of this energy efficiency index for new ships, and we also have this voluntary verification of energy efficiency design index for new designs. This is the so-called EEDI. All vessels that build right now and from now on have to comply with this regulation. You have to estimate this EEDI for the vessel that you are building or that you want to design. And the basic idea is that the numerator is the CO2 produced by all ships' energy systems, like auxiliary engines, main engines, waste heat, and shaft motors and others. You take into account measures that can reduce emissions. In here, in the efficient design options, and the denominator is the ton miles by the ship. And your goal is to achieve a low EEDI. And the era of non-regulation of greenhouse gases, actually CO2 emissions, ended when in 2011 IMO adopted this EEDI, which sets an upper bound on how much the EEDI of a ship should be. So you calculate this reference line, that's for bulk carriers, that's for container ships. You have the EEDI of your vessel. If your EEDI is below that baseline EEDI, then it's okay. If not, you have a problem. And right now there are some limits which will change, and we will have this baseline actually going down and down and down, so we have more strict rules regarding EDI. That's for new designs. For existing vessels, there is nothing mandatory. I mean, the EOI, which is, I may say, this, a similar index to EDI, the EOI is voluntary. What is mandatory for existing vessels is to have this Ship Energy Efficiency Management Plan, which is a document that contains a list of measures to make the ship more efficient. There are no efficiency targets associated with it. It's just only for reference. It contains, as I said, some measures for the crew or for the shipping company that they could implement to reduce mainly fuel consumption in order to have more energy efficient vessels, and as a result vessels that do not emit so much. The energy efficiency operational indicator, it's a notion somehow similar to the EEDI. EEDI is an index, EOI is an operational indicator, it's not an index. It is like a key performance indicator which takes into account the total fuel consumed, the actual distance traveled, and the cargo mass or the cargo units like TEUs or passengers that the ship carries, and you can estimate this EOI, this index or key performance indicator. And this is not mandatory. It's something that your company can do, and you can see how measures that your company implements affect the this CO2 index. Now, concluding this presentation with the so-called market-based measures. Market-based instruments was actually how we referred to these measures some years ago. And they are mainly related to the economics of externalities. You know, probably that fuel consumption, the amount of fuel that you consume, is related to the bunker price. In your everyday life, the amount of alcohol that you consume or cigarettes that you smoke is related to the price. If the price goes up, it means that the consumption will go down. At least that's what economics are saying. Emissions are considered to be a negative externality. It's an externality, it's something, it's negative because we don't want this. It is an externality because it's something that, like air emissions, are something that we do not take into account when we make decisions. So, when a company consumes fuel, the amount of fuel that is consumed is this one. It has to do with the supply and the demand, and mainly has to do with the bunker price. But the bunker price does not take into account the emissions that it produced. That's how the notion of externality comes in. So, the social cost is mostly is also taking into account the externality. I mean, if you include the cost of air emissions in your decision making, the optimum, the market equilibrium, which is actually here, that's the equilibrium, without taking emissions into account, moves to another point here when emissions are taken into account. In the case of a tax, if you set a tax on something, like a tax on fuel consumption, it's like setting a tax on the consumption of alcohol, for example. The tax sets a price on pollution. And this, together with the demand curve, determines the quantity of pollution that will be emitted. The point is that from an economics point of view, what we want to do in shipping is simply to put a tax. We don't call it tax, we call it a levy, but it's essentially a tax which will make the fuel price higher, and we hope that this will bring down the total demand of fuel. What we want to do is to force operators to use measures, operational measures or technical measures, to reduce fuel consumption so as to save paying money for taxes, which will also be beneficial for the environment. On the other hand, for example, aviation is included in the so-called emission trading, the European emission trading scheme. Emissions trading is also a solution to this problem, and what it does is the pollution permit set the quantity of pollution. We will issue some permits. One unit or one permit will allow you, the shipping company, to emit 1 ton of CO2. So you have a paper that gives you the right to emit 1 ton of CO2. If your company does not emit much, your company can sell this permit to another company that for them it's not that easy to reduce emissions. So you have a market, and this market works like this. You set the amount of quantity of pollution that you want. You say that I want to reduce emissions by that percentage. So in total, I want emissions, the quantity of emissions, to be 1 billion, let's say 1 billion tons. You set this. And this, together with the demand curve, determines the price of pollution. P is the price of pollution. This is how much the shipping company will pay per ton of CO2. So we have this externality, we have air emissions, we have the notion of external cost, a cost that is not taken into account because no one takes into account the fact that when we burn fuel it produces emissions, because the decision maker does not have to pay for the emission that the company produces. So we have two ways of reducing emissions with the so-called market-based instruments. One is setting a tax, as you can see in here, and the other is by having this emissions trading scheme, having these pollution permits that allow you to emit 1 ton of CO2 per unit. On the other hand, you have something that is probably more clear to you. You have a tax and you pay an amount of money, a fixed amount of money per ton of CO2 you emit, or actually per ton of bunker fuel that you buy. So the difference is that in the case of tax, we know, the shipping company knows what amount of money they will pay per ton of fuel they burn, but on the other hand, we are not sure what will be the total amount of CO2 that will be reduced. In the case of emissions trading, what we set is the quantity of pollution that we want, and we are certain about the amount of CO2 that we will reduce, but we are not certain about the amount of money that each permit will cost. So in the one case, the shipping company has a certainty on the price. In the other case, we don't have a certainty on the price, but we have a certainty on the amount that we will reduce. And that's the major difference between these two market-based measures. Why do we want a market-based measure? Because we believe that it will induce ship owners to adopt measures that will reduce CO2 emissions. We will also collect money to be used to reduce the emissions outside the marine sector. For example, we may give money to a wind farm in New Zealand, which is also another way, which is also probably a good idea to reduce emissions, but that's outside of the marine sector. And we may also use part of the money to support the least developed countries and to fund projects on research and development. So to conclude, this presentation presented you how to estimate shipper emissions. The formulas that I presented you can be used to estimate the amount of emissions produced by a single vessel, a fleet, by the total world fleet. It can be used to estimate emissions on a per trip basis, on a per year basis, or whatever you want. You just multiply the fuel consumption with the other factors that come into the questions as I presented you. Recall that the effects from air emissions are, that's a complex issue. Currently, we have negative effects from shipping, but this will change. The negative effect is mainly due to the cooling effect from SOx emissions. There was a discussion, actually a brief introduction on the emission regulations and the various measures and policies that can be used to reduce emissions. And last part of my presentation was on the so-called market-based instruments. And this was just a short introduction to shipping carbonomics. It's how the shipping economics are being transformed in this carbon-constrained world. For most of you, if you are about to graduate or if you just graduate, you have probably witnessed and you will witness a new world. Shipping, decisions are not mainly made based on the traditional economic criteria. There will be a shift on reducing emissions, on taking into account possibly a tax or a trading scheme that will be implemented, and all these things will become a major part of your decision criteria in the years to come. And emission is not the only environmental topic. We also have, for example, for tankers, oil emissions. We have also recycling, ballast water treatment. We have many environmental considerations, but emissions is the new hot topic. And I just said that this is just an introduction, and George Kapetanis, that just ended, is going to talk about this more extensively in his presentation that is scheduled for next Friday, if I'm not wrong. And he'll focus on things like speed reduction, emissions, the various regulations. And I invite you all, if you want to learn more on this topic, to follow his presentation on Friday. So actually there is a thank you very much slide in here, but let me just I have some 10 minutes, I think, so I'll briefly present you an emissions a ship emissions calculator that we have developed in the laboratory for maritime transport here at NTUA. This is a free web tool where you can go visit this website, enter the operational details for a vessel, like the speed and the fuel consumption in for fuel oil and diesel oil, and this web tool will calculate the emissions produced per round trip. You can change, you can use this mode with the predefined vessels, or you can actually enter, as I said, your own details, your own inputs, and the program will calculate and present you these detailed results as the ones you can see here, like the total consumption of fuel and diesel oil for the laden and ballast trip leg and in total, and the fuel consumption and the emissions. And here you can see the emissions. And here is the column with the emissions produced in the laden vessel, in the laden leg, in the ballast leg, at sea in port, and per round trip. And this emission calculator can also be used by companies as part of their corporate social responsibility to monitor and ensure that they are following what the law demands, and evaluate and report various indices, like the indicator, the operational indicator that I presented before. That's clearly something voluntary. There is no regulation regarding this, but this is something, I mean, you can use this emission calculator, and this is something that will benefit the company by knowing and monitoring how much CO2 you produce in your day-to-day operations, and it may help you to take some decisions on various measures that you can implement to reduce emissions. So, thank you very much, those here in the classrooms, and I also thank people that are watching this online. For some technical reason, we have to end the presentation right now, just before 2 o'clock. We may have to change to another room. In let's say 20 minutes approximately, there will be the second part of this presentation, also in environmental stuff. That's the new hot topic. So we'll have the introduction to carbon, to the shipping carbonomics, part 2, and that presentation will deal with speed optimization. I mean, it will be a brief introduction to speed optimization, and the relative problems that are raised due to implementing these operational measures, like the increase in time, like the constraints we have from charter party speeds, and the various market barriers that are related. And I will conclude that presentation with the virtual arrival incentive. It will be a very short introduction. I think it will be like 30 to 40 minutes. So again, thanks for being here. Are there any questions before we change to another room? Yes.
First of all, congratulations on your presentation. I have two basic questions. One, where will the levy tax be paid to? Governments or to IMO?
Yeah, that's an interesting question. We are not, right now this is under discussion. Yeah, for those that haven't listened to the question raised by the audience, I was asked who will pay the tax, if there will be any tax. So will it be paid to the IMO, or what's your second, or to the government? So my answer is as follows. If there will be a tax, it will be mostly a tax on bunker consumption. I mean, we can't go into like just measure the emissions produced in a vessel. But for sure, given the bunker delivery note, we know how much the quantity of fuel that was purchased by the vessel. So the easiest thing is to have a tax on that transaction. So the owner will pay an increased fuel price to the person, to the bunker supplier, and the bunker supplier will eventually, let's say per year, give that money back to the fund. It will be governed, I assume, by the IMO, but not belonging to the IMO. We have something similar. There is a similar fund that collects money for protection to cover cases of accidental spillage of oil. We have something similar, so in that case, and I assume we'll have a fund that is actually governed by the IMO. It will be a separate entity, but that money will end to that fund, and that fund will probably be responsible for giving this money, some of this money, to the least developed countries, or to fund research and development projects. And the other, this is your second question.
Whether you think that we can supply electric power from England, because a great amount of emissions are emissions produced by electric generators working when ships are berthed alongside, and way to unload this can before 3 or 4 days. So if we can supply them with electricity from land so that their electric generator won't work.
Yeah. So this second question is related to the so-called cold ironing, and I assume what you are asking is if I believe this will be. Sorry?
This is about.
Yeah. If this is something that will be, yeah, it's happening right now, especially in the US. But I don't know if this will become extremely popular. And I can say this. When you produce, I mean, in Greece, we have this thing, we produce electricity from burning coal. And this is the worst power of energy that we can use. In Sweden, for example, they produce electricity from total carbon neutral sources. So in some cases, receiving electricity to run the auxiliary engines does transfer the problem of ship emissions from the vessel to the source that produces the electricity. But if you're talking about cases or electricity produced by energy that produces no emissions, it's something that will be very beneficial for the environment, but there is an extreme cost associated with these investments. And currently, these investments are not cost effective in most cases. Cold ironing is mostly used for cruise vessels. It can be beneficial for them and for container vessels. Currently, there is a problem that facilities to provide electricity are not available worldwide, only some specific ports. So if you have a vessel that trades frequently from port A to port B and both ports can provide electricity, then in that case it will be beneficial. So if this is the norm in future years, if this becomes more cost effective, it is something that I believe will be implemented. For sure, it's a technology that can be used. It's a good solution, but it's a costly solution. And that's the only problem. I mean, actually not only, I mean, one problem is that you can't get power everywhere from electricity. But even if we had ports willing to provide electricity coming from sources, I mean, producing electricity from sources that itself produces no emissions or actually reduced emissions, it will be beneficial, but not for all vessels. Other questions? No. Okay. I think we can end this presentation right now. We'll change to another place. Yes. So we'll start next presentation in, let's say, 15 minutes. Is it okay?
Yes.
In approximately 15 to 20 minutes. Okay. So thank you and see you soon.